All right, these rascally game situations, how do we handle them? Interesting fact, probability itself came out of gambling and game situations several hundred years ago. So it has a history rooted in these types of problems. So how do we do this? If you throw exactly two heads and two tosses of a coin, you win 101. If not, you pay me $30. I'm going to pull in a spreadsheet again. And my point here is if you've watched the previous video on calculating expected value, we don't even need all this stuff. But that idea of getting x and p of x, that's really what we're doing here. Let me, could have copied these cells here. Um, so what are the different x values that I get? Well, win, I'm going to count as a positive, so I could get positive 101. Or paying someone else, that's a negative, so I'm going to put that as negative 30. Those are my only two x values. The only difference here is before I was given the probability, and now I need to come up with the probability. So what's the probability that I'm going to win 101? Well, I'm going to toss a coin twice, half chance of getting ahead each time, and I need to throw exactly two heads. Well, there's a half chance of getting ahead on the first one, a half chance on the second one. Multiply those, I get 1/4 or 0.25. Another way we could think of it is there's exactly four equally likely outcomes. Head, 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 tail, tail, head, tail, tail. All four of those are equally likely. That's important. And only one of those would get me a win. So that means the rest, probability has to equal 1 of all the possibilities. So the rest of the probability is that I'm going to lose this 30. And at this point, I do the same thing I did before. For expected value, I take the chance, how much I would win, times the chance of winning that, drag that over, do the same thing for the losses, and then I'm just going to add those up again. I'm just finding the expected value in the same way that I did before, except I needed to come up with the probabilities. And that gives me $2.75 for a single game. That's how much I would expect to win in a single game. Then they're going to ask me if I played this game 559. And believe it or not, when probability was being discovered, they would play this all the time. So I mean, a person would be like hired to just sit there and flip a coin all day long. So the 559 is very possible. Well, if I'm expected on average to win $2.75 per game, and I'm playing 559 games, all I have to do is multiply this to get my expected value. Same if it was something I was going to lose my expected value, then I would just take that negative number times however many times I'm going to play the game. So here I have 15, 37, 25. And it says losses must be expressed as negative, but this game worked out well for me because I was going to win a little bit every time, and then when we really magnified it by multiplying by 559. Okay, so here's another one. Let me just show you. I'm even going to, since I put these all as formulas here, all I need to do is adjust the formulas. So how much, I could either win $20, I'm going to put that here, or I could lose $26. Now I need the new probabilities. What's the chance that I win $20? Well, we're going to assume that this basketball player's rate continues. So if he's made he or she has made 294 out of 359, the probability of making the next one is probably 294 divided by 359 again. And then if we need to do that 3 times in a row, we're going to multiply it by itself 3 times, the shortcut being raising that to the third power. Excuse me. I could also do multiply 294 divided by 359 times 294 divided by 359. So I'm going to go ahead and do that. Remember, the probabilities have to equal 1, so I'm just going to do 1 minus whatever that probability was. And notice everything adjusts here. So in general, I'm going to lose 73 cents per time here. And I'm going to round that 3 up to a 4, and then go next. If I play this game 877 times, so here for this formula, all I have to do is change that 559 to 800 and what was it, 77. That'll give me my new updated value. I'm not liking this game nearly as much as the previous one. Round to 2 decimal points, so I'm going to lose about $640. That's what I can expect to lose. Okay, I have one more very similar situation. In fact, I'm just going to use the same table again. So what could I do? I could win 583. That's one of my possible values, or I could lose $35. So what's the chance that I win 583? So I have to draw 2 cards without replacement. That's important. If both cards are clubs, so I need to get 2 clubs. Well, there's 52 cards in a deck, and 13 of them are clubs. If you don't know that already, write that down in your notes for any future certify or tests or exams. 52 cards, there's 13 clubs, 13 hearts, 13 diamonds, 13 spades. I need to get a club on my first time, so that would be 13 divided by 52. And then instead of squaring it, because it says without replacement, if it was with replacement, if they put that card back in, then I would just multiply this by 13 over 52 again. But now because one of the clubs is missing from the deck, now there's only 12 clubs left, and there's only 51 cards in the deck. So I'm going to multiply that by 12 over 51. And because I set up this probability to already be 1 minus this probability, it automatically adjusted. The product's automatically adjusted. So I'm going to expect to win $1.35. Let me round that there. $1.35 per game. And then if I play this 632 times, again, I just need to adjust how many times I'm playing it here, 632. And so I would expect to win $855, and we'll round that up to the nearest cent. Okay, so this is essentially what goes on at casinos. Obviously, they're going to calculate, so they're making a little bit every time. And then since there's going to be thousands and thousands and thousands of games played on any given evening, they can be pretty sure that they're going to win quite a bit of money. As they say, the house never loses. Now, this isn't going to always be, if I played 632 times, I probably would not walk away with exactly $855.06. That's where the variance comes in, the calculation we did in the previous video. So we can know our best guess, our expected value, but also the range in which we can pretty seriously depend on winning or losing some amount of money.